Hello and welcome back. This will be the final section in Chapter 6, Section 6.6. And this is going to be about relating binomial distributions and normal distributions. In essence, they look very similar, and we can approximate binomial distributions using normal distributions. So we should remember what a binomial distribution is. We are going to be looking at a number of trials, and we want each trial to be the same and independent of one another. And what we're doing is we're looking to see whether or not something happens in each trial, and we'll call when that happens a success and when it doesn't happen a failure. So for instance, we could be flipping heads or flipping coins and counting how many heads we get. Each heads would be considered a success, and each tails would be not. Or it could be rolling dice, and maybe each 6 that we get is considered a success, and everything that's not a 6 we get is called a failure. So we are in a binomial distribution. We fix the number of trials. So for instance, how many coins we flip or how many dice we roll. For x, this is going to be how many successes are we going to count in that number of trials. So for instance, we might calculate the probability of flipping 48 heads out of 100 coin flips, or something like this. P and Q are going to be the probability of getting success and probability of getting a failure. So in a coin flip, both these will be equal. For dice, rolling a 6 would be less likely than not rolling a 6. But because the successes and failures are complements of one another, if you don't get a success, you must get a failure, and vice versa. The probability of getting a success is 1 minus the probability of getting a failure. Or another way to say this, the probability of getting a success plus the probability of getting a failure should be equal to 1. So if we look at sort of how these probabilities are distributed, if we look at, let's say we flip a coin 4 times and we count how many heads we get, we can see that the probability of flipping a 2 is about 6 and 16. Probability of getting a 1 or a 3 is 4 and 16. Probability of getting a 4 or a 0 is 2 and 16. And this kind of looks like a normal distribution. But it's quite blocky. So here, when we look at the normal distribution, the binomial distribution, we have these blocks because the binomial distribution is discrete. You can only get a 0, 1, 2, 3, or 4. We can't get anything in between, so it looks rather blocky. However, if we have more trials in our binomial distribution, say in this case if we were flipping a coin 20 times, we can see that it slowly becomes a little bit more continuous. It looks more like a binomial, it looks more like a normal distribution. It looks more like a bell curve. The more and more trials we get, the closer it is. And again, we still have this sort of blocky shape where in a binomial distribution we can only get these whole numbers of successes. We can only get, say, 17 successes. We can't get 17 and a half successes. Whereas in a normal distribution, normal distributions are continuous, and we can get any number along the distribution. So if we are going to approximate a binomial distribution using a normal distribution, there's a few things that we'll have to keep in mind. One is we'll need a lot of trials before it becomes close, before it becomes smooth enough to really approximate. And the other thing is we have to keep in mind that the binomial distribution is discrete, whereas the normal distribution is continuous. The binomial distribution, you can only get these whole numbers of successes, and normal distribution, that's not the case. So we need to keep this in mind. So if we're going to approximate a binomial distribution using a normal distribution, so it's a normal approximation to the binomial, there's 2 criteria that we have to have to satisfy. First of all, we have to start with a binomial distribution. So we need a simple random sample of size n from a binomial distribution. You need to know what how many trials there are, which is n, and the probability of success p. Once we know the probability p, we can figure out q. And the second condition here is saying that we need enough trials so that things are approximately smooth. So from before, when we only had 4 coin flips, it was pretty blocky and it didn't look like a normal distribution. When we had 20 coin flips, it started to look even better. So the criteria here, we need, put this in a different color, we need n times p to be greater than or equal to 5, and n times q to be greater than or equal to 5. So the expected number of successes needs to be bigger than 5, and the expected number of failures needs to be bigger than 5. If you only expect to get 1 or 2 successes, that's not enough. So bigger or more trials is going to be a more accurate approximation. So sometimes they suggest maybe even using 10 here, or however many you need before you can guarantee your trials are going to be approximately normal. So what are we actually approximating? Well, we know that the mean, so this is the mean of a binomial distribution. And instead of just treating it as a binomial distribution, we'll just go, oh, we're going to think of this as a normal distribution. So we're just going to use the mean that we can calculate here and just say, oh, it belongs to a normal distribution. Likewise, the standard deviation of a binomial distribution, which is written here, so it's just the square root of n times p times q. Rather than thinking, oh, I've got a binomial distribution with this standard deviation, we're going to go, nope, we're going to think of it as a normal distribution. So when we say that we're approximating this as a normal distribution, we're taking the numbers from the binomial distribution and plugging them into a usual normal distribution. And the last thing that I want to mention is this continuity correction. So, like I've mentioned before, the binomial distribution is discrete. So, for instance, the probability of getting a 2 in the binomial distribution should be given by this area right here. But when I look at this, this is actually stretching from this number, which is 1.5, up to 2.5. So if I were to try to look for this area in the normal distribution that is roughly approximating this, what I want to do is I want to go from 1.5 up to 2.5, and I want to calculate this area here. This is the approximation. So we have to keep this in mind. If we want a single value in the binomial distribution, it has to be an interval in the continuous normal distribution. So we're just going to go from 1/2 below to 1/2 above to represent that number. Let's go through some examples. So let's use a normal approximation to determine the probability of flipping exactly 10 heads out of 20 tries. So let's write a few things down first. The number of trials in here, n, is going to be 20. The probability of success, well, when we're flipping a coin, assuming it's a fair coin, the probability of success would be 0.5, and the probability of failure is also going to be 0.5. So the mean number of heads, the expected number of heads that we would flip in 20 tries, this is going to be n times p. So 20 times 0.5 is going to be 10. We'd expect to flip 10 heads out of 20 coin flips. The standard deviation is the square root of n times p times q, which is going to be 20 times 0.5 times 0.5. So this is half of 20 is 10, half of 10 is going to be 5. So this is the square root of 5. This is approximately 2.24, but I'm not going to round this for the moment. So I want the probability of flipping exactly 10 heads. Now, when I say 10 heads in the binomial distribution, this makes sense. In the normal distribution, however, I have to use my continuity correction. So rather than looking exactly at 10, I'm going to go down from 10 by a half and up from 10 by a half. So this will be 9.5 up to 10.5. So instead of calculating the probability of exactly 10 heads, I want to look at the probability of flipping somewhere between 9.5 heads and 10.5 heads. This doesn't make sense in the binomial distribution, but in the normal distribution, this makes sense. So I have to put everything into a standard normal distribution, so I need to calculate some z-scores. So again, the mean should be 0, and what I need to do is calculate the z-scores of 9.5 and 10.5. So for 9.5, I'm going to take 9.5 minus the mean, which is 10, and we'll divide it by the standard deviation, which is going to be about negative 2.236. And if I look at the z-score for 10.5, I take the value 10.5, I subtract it from the mean, and I see how many standard deviations away is it. So, and this is going to be about 0.2236. Notice that this is just the negative of this one because we're the normal distribution is symmetric and we're just on either sides of the mean. So what I want to do is I want to calculate the area between negative 0.2236 and 0.2236. So to calculate this area, there are a couple of ways to do this. I'm going to open StatCrunch. We can open up our calculator for our normal distribution. And one thing I didn't realize until recently was that rather than using the standard calculator, we can look at the calculator that calculates between. So I want to know the probability getting between negative 0.2236 and 0.2236. And here is our probability. So 17.69%. So the probability of x being between 9.5 and 10.5 is equal to 0.176.